Hello, everyone. In this video, we're going to start our notes for section 2.6 on the derivative of inverse functions. So far in this class, we've learned a lot of techniques and shortcuts for computing derivatives of products of functions, quotient functions, also composition of functions. But now we look at computing derivatives of inverse functions. And so to get started, let's just review some facts and information about inverse functions. So let's recall that if a function, let's say labeled f, goes from a set A to B, then a function that has an inverse, then this function has an inverse function that we call f to the -1, which goes from B to A. So it goes in the opposite direction. So a few facts here. The point xy is on the graph of y equals f of x. If and only if the point yx is on the graph of the inverse y equals f -1 of x. So graphically, what this means is that any point on our original function, so I'll identify a point here maybe, at over 1 up 2, is going to be on the inverse function, but it's going to be up 1 over 2. So if we kept doing this with all of the points on our original function, then what we get is the inverse function that looks like a reflection across this x equals y line. And we can even write that out if we want to be more clear. So here, this point is on our original function at 1, 2. Here, that point is on our inverse as 2, 1. The x and y values switch on the inverse function. Another fact about inverse functions is that for every number x in the domain of f, and for every number y in the domain of f -1, we have that the inverse function, f -1, applied to the function f undoes the function. So the output we would get is x in this case. And then similarly, if we started with a value y in the input of the inverse, then if we apply the original function, we're going to output y. So again, this fact number 2 emphasizes that the inverse undoes the original function. Another picture I often like to draw of functions and inverses are the sets A, B. So if A is our domain, B is the output of our original function f, then the inverse function goes in the opposite direction and undoes the original function. So let's look at an example of how we can use inverse functions to compute derivatives. So let's take a look at example 1. Given to the right is a graph of the function ln of x, so the natural log of x. First, we're asked to draw a sketch of a rough graph of f prime of x, the derivative, and then derive the formula for this derivative. So what I'd like you to do is pause the video right now, and using this graph of f, see if you can sketch in what you think the derivative should look like. If you need help getting started, one thing you can think about is, first of all, what will the sign of the derivative be at any point? Is it going to be positive or negative? So please pause the video now if you haven't already. After you've had a chance to do that, please continue on and we'll look together. So we can see that our function f, if we drew in some kind of sketches of tangent lines here, all of these tangent lines have a positive slope. So our derivative f prime is always going to have to be positive. F prime is going to be positive. All right, but what will the shape look like? Well, if we do sketch in some of these tangent lines, I'm going to sketch in so they last for us. We see that the slope starts out very steep here and then gets smaller and smaller and smaller. So our derivative should start pretty high because we start with a large slope, and then get smaller and smaller and smaller. Maybe even goes close to 0 as we get out here. So using the graph, we see that the derivative f prime should look something like this graph I just sketched here in orange. All right, so now let's go about actually computing what that derivative is. So we don't have a formula so far for the derivative of ln of x, but what are some things we know about the ln of x function? So one thing we know about this function, and that's okay if this doesn't sound familiar, it might be something you've seen in a previous math class. But one thing we know about the natural log function is that it undoes the exponential function. It's the inverse of the exponential function. So if I start with an x and I have the exponential function e to the x, I output e to the x. Then if I want to go back, I do ln of e to the x to get back. So this exponential function goes in one direction and the ln function undoes that operation. So in other words, what that means is that I can write e to the ln of x is just equal to x. The exponential undoes the natural log undoes the exponential. So we know that we have this equation. This equation is true. So why not? Let's take the derivative of both sides. All right, let's do that. So what happens? So we take the derivative of the left side is the derivative of e to the ln of x. And the right side is derivative of x with respect to x. So now let's look at both sides separately. So we see that on the left side, we have a composition of the exponential function e to the power. And inside that function, we have another function, ln of x. So let's call that inside function u. And we can recognize this left-hand function as a composition. And so we need to take the chain rule. So to do the chain rule, we do the derivative of the outer function. So derivative of e to the u, that's just going to be e to the u. So I'm going to have e to the, and my u is ln of x, times derivative of that u, derivative of ln of x. And then now the right side, the derivative of x is just 1. And recall that we can just use the power rule, exponent 1 there. And that's also one that maybe we just have written down or memorized at this point. All right, so now let's sort out what we have. Well, here we don't have any derivative going on. We just have our e to the ln x. Here we have derivative of ln of x, which is what we want to find. Then here we just have a number, no big deal. So at this point, what we can do is solve for this unknown that we're trying to compute. So to do that, we can divide both sides by e to the ln of x. That e to the ln of x will then cancel on that left-hand side. So now, what do I have? Well, I have the derivative of ln of x with respect to x is equal to 1 over e to the ln of x. And now let's just recall, as we started, we know that the exponential undoes the natural log. So down here, e to the ln of x, that's just equal to x. So this just becomes 1 over x. And so now we see that we have a formula for the natural log of x is just 1 over x. So I can get rid of that middle part, and I can summarize that the derivative of ln of x with respect to x is just equal to 1 over x, 1 over the inside part there. So we can do a nice box around that formula. And then now let's compare what we just computed with our sketch of the derivative here. So we found that f prime should be equal to 1 over x. And let's see, does our graph look like that? Well, the function 1 over x, we're dividing our input, or we're starting with 1 and then dividing our input. So the smaller the input, the larger our output. And then as we get a larger and larger output, this value 1 over that input gets smaller. We're taking 1 divided by a larger number. So we're essentially breaking up our 1 into smaller parts. So yep, we should get smaller there. Feel free to graph, take a look at that graph 1 over x as well, and graph it on the same axes as ln of x. And you can see that indeed, it looks like it's a good fit for the derivative. Awesome. All right, thanks for your work, everyone. Please feel free to rewatch any parts of this video to help deepen your understanding. And I'll see you on the next one.